program tonight, Frank and Neil, and digital radio technology.
Basically, the program's going to be divided into 3 parts. I have a few slides here. We're going to talk about what the heck is a digital radio anyway. And the main program is about the DMR format of digital radio, which was introduced in the United States by Motorola as their Moto Turbo product, but it is based on a standard. It's produced by many companies, and it's the most popular commercial format on a worldwide basis. So, if I can remember which button to push on this clicker, this is a block diagram of a digital radio, and we're talking about VHF and UHF kind of radios as opposed to the kind of digital radio that you have on HF. There's some fun modes down there, but that's kind of an entirely different technology. So what we've got in a VHF and UHF radio is an operational characteristic that's very much like an FM radio. FM radio is what developed the use of portable and mobile radios for all sorts of things. And that's where we have our 2-meter 440 repeaters, simplex traffic, and quite a lot of activity in that way. In a traditional FM radio, your microphone would talk basically through an amplifier stage and directly over to the filter and into the modulator and out to the antenna. And here we have, in a digital radio, we have some additional elements. We have a speech coder and a channel coder. Now, everything has gone digital these days. So when we start in a digital radio, we have analog to digital conversion, and then we don't have enough bandwidth on our radio channels to just put all of that data that results from the A to D conversion right out and modulate the channel. We have to compress it somehow. Pretty much a universal thing with digital systems is that they start by digitizing and then they compress the data in some way. So with audio, it'd be like an MP3, and with video, you got MPEG. With photographs, you got JPEG. And all of these compression techniques save the storage or channel bandwidth requirements down to narrower amounts so that we can fit a lot of information into a smaller space. So the receive process just kind of reverses, and we take the signal off the air through the receiver. That part of the radio is the same as an analog radio would be, and then we take the digital data and recover the speech. So, to elaborate a little bit more on what goes on inside of the digital part of the radio, we have our analog input from the microphone goes through our input gain. Then we have a filter that removes the areas of the spectrum that are outside the voice range. And then we go into the A to D converter and we pass this on to a device that's known as a vocoder. That's a voice coder. There are several variations of this, but virtually all digital voice systems use some sort of vocoder. Your cell phone, for example, uses a vocoder. They're not always the same. The two-way radio vocoders are a product of a company called Digital Voice Systems Incorporated, and it's a patented technology, but it has pretty much been universally adapted by the majority of the digital voice two-way radio type systems. The cell phones use other types of vocoders, adaptive multi-rate. They all have a fancy name for them. AMBE stands for Advanced Multi-Band Encoding. This is a block diagram of the AMBE vocoding chip, and this is the chip that's used in a D-Star radio. And if so, I'm sure we've heard of D-Star, and one of the things we'll talk a little bit about in this preliminary is a little bit of the differences between the D-Star and the DMR, and then Frank will get into a little more detail on that. This is used in D-Star radios. The DVSI company will sell you that chip for like 20 bucks. It contains the vocoder and a lot of other support circuitry, and in particular it contains what's known as forward error correction. When we're transmitting digital information through some circuit path, sometimes there are imperfections that creep in there. If you're dealing with a computer, you might remember that we have things like parity bits and checksums and such as that. And so we had protocols for data transfer. If you might remember X modem and things of that nature. You send a block of data, and at the other end we compare the checksum. If there's a problem, we say, hey, send that block of data again. Well, that won't work in a radio because we have to work in real time. So they use what's called a forward error correction. Part of the bandwidth of data that we're sending is redundant information, not an entire duplication. So if we have a channel that can support 9600 bits per second, out of that we may allocate 2400 or 3600 for voice, and then maybe 1200 for error correction. And a point of interest here is that this vocoder chip, the one that ICOM used for the D-Star, has this error correction built into the chip. And it's a generic kind of chip. So you can see here that they say that this can be used with RF, FM, satellites, and so on. So it's a kind of a generic error correction. We'll talk a little bit more about that later, where the other formats of digital radio, like DMR, they error correct as a part of the protocol instead of as a part of the voice payload. And so D-Star only error corrects the voice payload. They don't error correct the rest of the data, and these other formats error correct the entire format, and that can be significant, as we'll see a little bit later. So can all the digital radios talk to each other? Well, unfortunately, no. There are all these different formats. Now, a format consists of several elements. You have the type of modulation, C4 FM. And sometimes that can be very confusing for people because, well, for example, Yaesu says their system fusion is C4 FM and P25 is C4 FM. But they won't talk to each other just because they're C4 FM. That's just the way that the digital data is put onto the RF carrier. And another facet of that is the data rate. How much data are we transmitting? Like a P25 is 9600 bits per second. The protocol is basically what we're going to do with all of that data. And that defines the arrangement of the data, and some of it is going to be for voice, and some of it's going to be for the error correction, and some of it's going to be for other stuff that we're going to transmit along with it. Collectively, those become the air interface. You'll hear that term or see that term in connection with digital radio systems. Air interface represents all of that technical stuff that goes into the format. So what kinds of formats are hams using? Now, there's a few more formats that came along, have come and gone, but these are the big formats that exist, that at least there's some hams playing with them. Now, the P25, NXDN, Yaesu System Fusion, D-Star, and DMR Moto Turbo. P25 started out a long time ago, 15 years or more, initiated by APCO, which is the Association of Public Safety Communication Officers, and their objective was to develop a standard so that radios for public safety would all be able to talk to each other. It's used by a lot of large public safety systems, including what's known as Orion, the Omaha Regional Interoperability Network, the OPPD, Douglas County, Washington County, Potawatomi County, and so on. There are many companies that make radios, so it's fun to play with because you can get all kinds of cool radios. It's an excellent interface in terms of its performance over the air. There are some ham repeaters. I have one in Sarpy County, works wonderfully. It's fun to play with, but not a lot of traffic. And there's only a minimal amount of wide area linking been done so far by hams with P25. And that's kind of significant because that seems to have become one of the attractions of the digital radios for hams, is the fact that you talk to people all over the place. So that hasn't been a part of P25. NXDN is another format that's a joint standard with ICOM and Kenwood. It's based on ETSI DPMR. Now, ETSI is the European Telecommunication Standards, and DPMR is one of their standards, and DMR, that Frank's going to talk about, is another one of their standards. It's been introduced by ICOM and Kenwood relatively recently, and it's a true 6 1/4, very narrow band. We'll talk a little bit about bandwidth. It's being adopted by the railroads, the U.S. Railroads, Association of American Railroads, and so that means there's a lot of use in the commercial area, and so naturally some hams have picked up on that, and there's about 30 ham repeaters at this time linked together around the world that use NXDN technology. So now, another one you will see, if you get QST and open the front cover, you'll get splash of multi-pages from Yaesu System Fusion. And that's very late to the digital market. All the rest of the formats, DMR, D-Star, been around for years, but they come along, and the reason that people are calling it system confusion is they introduced this paper several years ago, and they talked about how they were going to have the world's greatest radio. And basically they wanted, I think, to sow confusion so that people would stop buying other stuff and wait for them. And so it talked about P25, and so a lot of the P25 hams are going, oh boy, this is going to be great, I'm going to wait and buy one of those. And if you can still download this paper, and it talked about DMR and the DMR Mark group and the Moto Turbo, and a lot of people say, oh boy, it's going to do DMR, I'm going to wait and buy one of those. Well, now here it is. It doesn't talk to any of them, doesn't talk to anything except itself. It's a neat format. It's got some neat features. I think if it had come out first, we wouldn't be having this meeting, because that could have been the one and only ham format if it had come out first. It's that cool. But there's only a couple of repeaters in existence right now, and they're on beta test from Yaesu. And I really would be surprised if they get enough traction to become a major player based on what else has gone on. Now we got D-Star, which we know was designed by hams for hams. It's a Japanese standard, and I'm a little disappointed that our own American Radio League wasn't a more prominent player in the development of a digital standard for U.S. hams. It was introduced in 2005. It does have extensive wide area capabilities that to me are just very confusing, because you can have call sign routing from one guy to another, and the network knows where he is and it finds him, and you can have repeater to repeater routing, and you can have reflectors, and I don't know how you know where you're going, but basically there's only one company that makes radios for D-Star, and that's ICOM. And that bothers some people, it doesn't bother me. I like ICOM radios, but there's also this company, Connect Systems, has promised a dual mode DMR and D-Star radio, and I think that'll go a long way to getting people to jump into digital radio if you can get a radio that'll talk to more than one kind of system. The D-Star interface over the air, not so effective as the other formats, principally I think because of that forward error correction issue that we'll talk to. Now, there's about 1,000 gateways involved in the worldwide D-Star arrangement. And they'll tell you there's at least a couple of thousand or more repeaters. Basically, a gateway is an endpoint that has an address in a network and one or more repeaters. And in the architecture of D-Star, you've got a gateway, which is a computer running a software program that's attached to a controller that's attached to one or more repeaters that are attached to duplexers and antennas and so on. And a lot of people have what's known as a stack. And I'm not sure about the one that's here on the big tall building. if it's got both a VHF and a UHF, but that's when you put a power supply and a controller and a gateway and a couple of repeaters, you wind up with a stack. And so in terms of how many places you can talk, the fact that there's like 2,000 repeaters, it's more like there's 1,000 locations, and in most of those there's 2 or more talk paths because they've got 2 repeaters connected to the controller that's connected to the gateway. So it's more complex than the DMR, as Frank will show you. The DMR, that's the subject of the presentation. There's many manufacturers of radios. It has extensive wide area capabilities. It's the fastest growing ham digital format because it's only been fielded here for the last few years, and we're already at over 800 repeater sites worldwide, which I think is closing in on D-Star if they're really only at a little over 1,000 sites. And it's a very high performance air interface, which we'll talk a little bit about. So why would you use digital? Well, we're hams and we like to play with stuff and it's fun, so that's enough for most of us. But the companies that promote it will tell you that these are features of digital radios that go beyond what you have with an analog radio. You have improved spectrum efficiency, you have embedded signaling. So as you're transmitting, there's stuff that's being sent along with it, and additional features that are in the radio, and the wide area network routing, which is a big attraction for hams. And we have consistent audio quality. They're always telling you, wow, digital, it's consistent, it's wonderful. So we'll talk a little bit about that too. The spectrum efficiency, this is kind of a graph that shows very, very simple terms. This represents a 25 kilohertz channel that a traditional land mobile type radio, just like our VHF and UHF repeater, ham repeaters use. The commercial world has all been forced by the FCC to achieve half the utilization or narrow band, which is 12.25, and then there's some interest by the FCC in going to a 6.25 utilization, which would give you 4 times as many conversations in the same amount of spectrum that one traditional, now known as wideband type radio would use. So you'll hear a couple of terms in connection with digital radio systems that are thrown around, and those are FDMA and TDMA. And the one that FDMA simply means frequency division multiple access. All that means is that we're having more conversations in the same amount of space by dividing the frequency. And we've been doing that as hams for years. Sideband, you can get, 3 times as many conversations in the same amount of spectrum as one old AM rig would have taken. So it's that simple. FDMA, that's all it means. TDMA, that's a little more complicated. Basically, you can't do that without being digital. It's a time division. So we can take one slice of spectrum of however size. In the case of DMR, we're using a 12.5 type spectrum, and we're interleaving the data from 2 conversations into that data stream so that we're getting the equivalent of if we were 6.25. So when you hear that TDMA, that's what that's all about. We're dividing the time in a very precise way. Now there are multiple formats in other types of systems other than DMR where instead of 2 slots they might have 4 slots or what have you. So just because something's TDMA, one thing TDMA does not necessarily talk to another thing TDMA. P25 phase 2 is a 2-slot TDMA. It will not talk to Moto Turbo, which is also a 2-slot TDMA because that's just part of the protocol. So that air interface that we talked about at the highest level, each one of these formats is unique. They don't talk to each other. Now, embedded signaling, what does that mean? We have a network access, just like you have a tone on your analog radio. So there's something that you put into that radio. It could be something that you put into a D-Star radio that says, I want to talk to this repeater, or we can put in what's known as a network access code or a color code, unit IDs and call signs. Each radio in a digital system can be uniquely identified to the system and to the other end, and so you can have, the radio will display a call sign or what we call alias information in these that can bring up the name of the person on the other end. Low-speed data, like D-Star, you can put in a certain number of characters, 20 or whatever it is, that transmitted continuously so the radio on the other end sees that. Some of the P25 radios can do the same kind of thing. And network routing information that we can put in there. With D-Star, we can tell the system through things that we poke into the radio where we want to go. And with DMR, we do that with talk groups and time slot choices that tell the network where we want to go. And those are things that you do seamlessly with a digital radio, whereas with maybe an analog, you got to DTMF up some Echo Link type of a thing. So now additional features, we can have texting directly from radio to radio, just like you do with a cell phone. And the DMR radios can do that. GPS location, a lot of the radios have that. ICOMs, I think some of the latest ones may have it built in. 92AD that I have, it has it in a microphone. Image transfer, System Fusion is talking about doing that. Telemetry, with DMR and some of the formats, I can send a signal from my radio and close a relay on another radio. Like I want to open my garage door, I could have a radio and I could just drive up the street, or I could open my garage door from Poughkeepsie, you know, telemetry. And a computer interface so I can hook up and transfer data and text applications with D-Star like DRATs. So those are features that digital radios have. And then they want to, with the wide area network, you know, that lets you talk all across of the world or some specific group or geographical subset. And any one local repeater can be a local thing or it can be part of something bigger. Now they want to talk about consistent audio quality, and that's a graph that you'll see associated with almost all these digital formats, and the manufacturers will all show you a graph that kind of looks like this. Every one of them has their own, but they all try to make the same point, and that point is that as you go away from the repeater, but here it says close, and over there it says far, and we have distance, and as you go away from the repeater, this line is an analog signal, and analog voice quality degrades gradually as you get farther and farther out, whereas digital is very consistent. Now you'll see that it starts out just a little bit lower in terms of quality, and then it gets out to the end and falls off. So that's something that's promoted as a big feature of digital voice radio systems. And so it raises the question, well, how do we measure that? Well, we can't test it the way we test a regular analog radio with SINAD, because of the way these voice coders work, they don't transmit tones. They recognize sounds, voice sounds and pitches, and they token that into a digital representation, transmit that across to the other end. Other end reconstructs the voice. So they don't deal very well with tones, although the latest versions have been specifically coded to allow you to transmit touch tone dial signals through there. They recognize and reconstruct that. So what they do is they find what they call a bit error rate, which is as the digital signal gets weaker and weaker, it starts to get errors, and they can measure the bit error rate, and they say, we're going to specify that this radio will operate down to a 5% bit error rate at minus 118 dBm or something of that nature. And then we have an audio quality that's equivalent to a certain bit error rate. So what the heck is delivered audio quality, DAQ? It's a scale of 1 to 5, whereas 1 is unreadable and 5 is easily understood. It's defined by the Electronics Industry Association, and for any of the techies, 12 dB SINAD analog sensitivity point is equivalent to a DAC2, and a 20 dB SINET is equivalent to a DAC 3.4. And to arrive at this, they did subjective testing and had people, large groups of people, listen to radio traffic and say how could they understand this, and they have recorded all these various levels of radio traffic. So now how do we actually test that vocoder to make sure it's doing the right thing? The company, DVSI, has created test files specifically for that, and it's built right into test equipment like that Aeroflex analyzer that's pictured there. And it simply transmits the same set of phrases repetitively. And these are designed to contain the voice sounds and pitches that the vocoder has to recognize and reconstruct. And so we've got a sample file that we downloaded from DVSI, and we'll play that so you can hear how that sounds, if I can get the mouse to behave here. And
they took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
now that's the standard file from DVSI. And then what we did was we took this file and we filtered it to eliminate everything below 300 hertz, because a typical two-way radio doesn't use that spectrum for anything except PL tones. And so this is what a two-way radio would normally sound like if it
They
was
took the crosstown
absolutely
bus.
perfect.
Don't throw trash on the street. These shoes were black and brown.
It's a little bit different than the file you would download over the internet, because we filtered out everything below 300 hertz. And that we're going to show you in a minute with some actual simulations.
They took the crosstown bus.
Get used to
Don't
what
throw
that
trash
sounds
on
like.
the
So,
street.
now,
These shoes were black and brown.
SINET and bit error rate, those are static tests. We set up a radio on a bench with a piece of equipment, a signal generator, service monitor, and static is not, that's a closed system. It's not subjected to any disruptions. But the real world doesn't work that way. The real world has noise and interference and multipath and fading, and picket fencing is what we call that. Anybody that's ever used a two-way radio in a vehicle, you've heard that. And in fact, we can simulate all of that with the right equipment. And this is an example of an equipment configuration set up in the lab to simulate the real world. We have what's a channel emulator here that can emulate the fading and multipath characteristics that we have in a mobile environment. We have signal generator, service monitor. This is a D-Star stack with a controller, power supply, D-Star repeater, and we have a digital Tascam digital audio workstation, a PC, and some ICOM D-Star transceivers here. And we duplicated this same process with Motorola radios as well as the D-Star in order to try to assess this. And I'll tell you why we put a D-Star repeater on the air in Sarpy County several years ago, and we set out to see how's this work, and we found out that we drive out away from the repeater, and we have a Motorola digital repeater on the same exact tower. The antennas are right next to each other, and we swapped the antennas, and what we found was the D-Star would have problems when we get nowhere near as far as we got with the Motorola. We try to understand why, so run this through lab tests to figure this out, and that's what we'll go through here just a little bit. Basically, the D-Star, you'll hear people that use D-Star say, well, you went R2D2, and we'll show you what that's all about. Here's another one of those charts that in fact has that DAC, the delivered audio quality representations on it. And what we've got here is these little PowerPoint speaker icons that will allow us to play an audio file. And the files that we've got show the matter of interest of what it sounds like when that signal is excellent, when you're close in. And then, rather than trying to listen to a bazillion of them at different places, we've got what that sounds like when you're out near the end of the world. A little more better than what a 12 dB SINAD would be, but in that general area. And so we'll see if we can get the mouse to cooperate here. Where's the pointer, Frank? There we go. All right. This first one I got is analog. Basically, this is a static test of an analog radio, one radio connected to the digital audio workstation, play that test file through the radio, and it goes over to another radio, and then it comes back and we record it and listen to it. And what we're going to do on the close in is we're just going to listen to the basic test file, and mentally we're going to compare what that sounds like to what the reference file sounded like.
They took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
Now that's our analog radio, and it sounds virtually identical to the reference file. And then our our digital radio. This is a Motorola digital radio.
They took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
And there's a little bit of difference. You can tell there's a little bit of harshness or a little bit of a metallic quality to it, but it's very, very understandable. So that's why these things score just a little bit lower in subjective tests. And then what we have here as the last test is a D-Star, which is going to sound very, very good, but there's a little difference in the audio characteristic of the ICOM radios that we, and I don't know that you could say that one sounds better, but you'll note it sounds different, but it's fully understandable.
They took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
And that's two digital radios with a strong signal. So now what we're going to do is we're going to go over and we're going to listen to what happens to the transmission when the signal isn't so strong. And get your mouse to cooperate. All right. Now we'll listen to the analog first. Now what we did here is we concatenated three tests. The first test is just a stationary user with a weak signal. And then we got a moving user. And first we use a moving user with what we call a fast fade. In the industry, the standards for the Motorola type radios, the industry specifies testing these at the equivalent of 100 kilometers per hour and 8 kilometers per hour for a slow fade. And you've all heard the fast fade is a picket fencing thing, and a slow fade is a and with your basic analog radio, with that slow fade, you got a problem. You either got the situation that we've got here where the radio squelches, or you could reach down and turn the squelch open, and then you'd hear noise in those fades. So this is kind of amazing. It sounds
They took the
exactly.
crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
They took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
They took the crosstown.
Don't throw trash on the street. These shoes were black and brown.
They took the cross bus.
Don't throw. Shoes were brown.
They took
That's
the
a slow fade, and
crosstown
that's
bus.
why people say the digital radio doesn't do that. Now, if we went down to where we had to open the squelch and we could just hear a little bit of audio, that the digital radio would be gone, and you might be able to pick up a little something with the squelch open. For the average user with the squelch set, this is what happens to you in a weak signal area. Now, this is what happens with the digital, and the first part of the digital is almost perfect. You may hear
That
just
was
a-
analog that you just
That was
did?
an analog radio.
Okay.
That was a pair of Motorola analog radios in the lab set up with that emulation. And it's just amazing how that box, it's $50,000 worth of DSP, can emulate, and it sounds to me just like what happens when you're out driving in the field. Now, we did the same thing with the Motorola digital radio.
They took the crosstown
And
bus.
this is a weak signal.
Don't throw trash on the street. These shoes
As
were
it starts to
black and
fade,
brown.
you'll hear a little bit of
They took the
jitter in it.
crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
They took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
They took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
They took the crosstown bus.
Don't throw trash in the street. These shoes were black and brown.
So, what happens is that forward error correction does the best job it can, then it hands the data off to the vocoder to reconstruct. And what it tries to do is say, if there's something missing or the data is corrupt, now look at what was I doing before I got to the bad part, and what am I doing after the bad part, and I'll fill it in as best I can. It gets pretty close. You can hear a little corruption, but when you do that with a D-Star radio, and you don't have to take my word for it, you can just, if there's a conversation on a D-Star repeater, you can unplug the antenna and plug it back on. It takes a while for D-Star to get on its feet. And there's a difference in the way that the data is synchronized. These synchronize continuously, and D-Star's format only synchronizes every so often. So if you lose sync because of a signal dropout, then the data gets completely misaligned, and there's no way you can error correct that. So this is the same basic exact signal level, same circumstances. And when we listen to the weak signal where it's stationary, you'll hear that there's a few jitters in there, but D-Star manages okay. It's when it starts to get faded that it gets, oops. All right. All right. This was the. Why is it not going?
They took the crosstown bus.
Don't throw. These shoes were black and brown.
They took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
They took the crosstown bus.
Don't throw trash on the street. These shoes were black and brown.
They took the crosstown bus.
Don't throw trash on the street. These shoes.
That's what people mean when they say, you went R2D2 on me.
These shoes were black and brown. Trash on the street. These shoes were black and brown.
So, part of Frank's presentation is going to talk about the error correction being very robust in DMR. These are the fundamentals, and we're not trying to say one format is incredibly better than the other, but in my observation, it seems to me that people that are into computers, they kind of really like D-Star because it's a network, and they can play with it, and they can make little doodads like hotspots and dongles, and it's been very interesting and fun for amateur radio. But I think you'll find that a lot of people that are radio people that have a background in any kind of public safety radio, two-way radio, whatever, are gravitating this way, and this is one of the reasons is that it's very robust in terms of its performance, and the network routing is a very structured, logical thing that you can just turn a knob on here and talk where you want to talk without having to poke a lot of keys and try to figure out how to get the system to do what you want it to do. So anyway, that is the basics of the technology underneath this, and if that's good, then I'll hand this to Frank, and he can start in with the DMR part of thing. And then the third part, of course, is that there's real radios here that you can actually talk on and listen to them and test and talk to people in Germany or Poughkeepsie or wherever.
DMR standard was published by the European Telecommunications Standards Institute, ETSI, like Neil's already said. And the organization was started in 2005 with the goal of providing digital communication systems that are low cost, low complexity, and interoperable between equipment vendors. The DMR standard specifies the air interface between radios specifically to use the following: two-slot time domain multiple access, or TDMA, 12.5 kilocycle channel width, 4 FSK digital modulation, and used on frequencies anywhere from 30 megahertz to 1 gigahertz. They all decided they were going to use the same common AMBE vocoder, and in order to promote the growth of the digital mobile radio market, the DMR Association was formed and consists of various stakeholders involved in the DMR ecosystem. In addition to promoting DMR, the association provides interoperability, testing, and certification of DMR equipment prior to FCC Part 90 approval. There are several manufacturers that build DMR radio equipment, including Motorola, Vertex Standard, Connect Systems, Harris, Hytera, Tate, Kerasun, Simico, and Kenwood. Kenwood entered the DMR market in Europe and Asia to compete with the other manufacturers, but they're only marketing their APCO Project 25 and the NXDN products in the United States. On June 9th, 2014, the Federal Communications Commission officially approved the use of TDMA and the modulation type used for the digital mobile radio for amateur radio use. In FCC Decision 14-74, the FCC outlined the decision to officially approve TDMA for ham radio use, as in doing so would be, quote, consistent with the basis and purpose of the amateur service, end quote. Why DMR? Well, it has superior RF performance. In high-speed digital mobile communications, transmission performance is severely degraded by frequency selective fading caused by the time delay spread of multipath propagation, which we have the demonstration. The DMR digital research provides better noise rejection and preserves voice quality over a greater range than analog, specifically in the farthest edges of the transmission range. The coders enabled receiving radios to detect and automatically correct transmission errors by analyzing bits inserted into messages that enable the receiving radio to tell if there's an error. The DMR standard specified over 14 different coders to be used. Each one's matched to the different type of traffic that is being transmitted. So that's why you get the forward error correction and why it's so good. Okay. The radios are affordable. The DMR is fully public open standard backed by a variety of vendors. The buyers can be assured of continuity of supply. There are many examples of the success of technologies incorporated into the open standards because standards encourage wide-ranging supplier participation. More suppliers result in more choices for users, more rapid product development, and lower prices from competitive pressures. We benefit from that. Extended battery life. Two-slot TDMA system is an individual call that uses only one of the 2 time slots. It requires only half of the transmitter's capacity. That's what saves you all the battery usage. I'm going to run through this a little bit faster. We're already getting for 9 o'clock here. Even though many factors affect power consumption in an individual device, comparing published battery life figures for widely marketed DMR and FMDA digital radios show the benefit of the TDMA approach over the FDMA. For each hour of usage, the TDMA radio shows about 19 to 34% less battery capacity. Roaming. DMR systems promote roaming technology. What this means is as you drive around or walk about and the signal strength drops on the repeater that you're using, the radio automatically can switch you over to another repeater with stronger requirements or capabilities. There's no need to touch your channel selector. It'd be hands-off just like a cellular telephone. The roaming feature is aimed primarily for mobiles who cover large areas. As a local example, let's say you're driving from Fort Omaha to North 30th Street, heading south to Lincoln, and you want to go from Lincoln to Nebraska City, then return to Omaha later in the day. You have your mobile radio set to a talk group of your choice. It could be worldwide, it could be North America, Midwest, or Nebraska only. The first DMR repeater you would have contact with is located in downtown Omaha near 480 and Harney Street. As you continue west on the interstate towards southwest Omaha, your radio would automatically switch to a DMR repeater located near Interstate 80 and 680. And as you continue west and reach the junction of Interstate 80 and Highway 31 south of Gretna, your radio would automatically switch to the Lincoln repeater that's located on a 14-story building south of Memorial Stadium. Upon completion of your errand in Lincoln, you would probably drive east on Highway 34 to reach Nebraska City. As you continue east on Highway 34, somewhere around the intersection leading to Elmwood, your radio would then automatically switch to the DMR repeater located on a tower in Weeping Water, Nebraska. And eventually you would be handed off to the DMR repeater in Nebraska City as you start south on Highway 75. When you finish your business in Nebraska City and decide to head north back in Omaha, your radio would automatically switch to the Weeping Water repeater for a time, and then you'd reach the area between Murray and Plattsmouth, and your radio would automatically switch to the DMR repeater in Bellevue. Eventually, as you continue north, your radio would be handed back over to the downtown Omaha repeater. TDMA essentially means that you've got two multipaths or two paths to talk on using the same frequency. It enables the DMR repeaters or radios to operate existing 12.5 KCs or 25 kilocycle channels, at the same time doubling the capacity of the channel. So if the Aksarben Amateur Radio Club would have a coordinated repeater, this could be greatly accomplished. Efficient use of infrastructure. As you can see here on the diagram, the top one, it would be a typical repeater used in DMR. You would have the repeater duplexer, and it would go to an antenna. Of course, you're not seeing the voice over internet protocol here with the connection to the internet. But if you want to do the same thing with, say, with an analog repeater, you'd actually have to have two repeaters, a power amp, combiner, multicoupler, duplex, and that sort of thing to accomplish the same thing. You'd also be using a lot more bandwidth. AM's adopted the Motor Turbo commercial DMR product for amateur radio, established in 2009 as an international Motor Turbo DMR repeater network. There were 6 people in the United States that got this thing started, and since that time it's grown outstandingly. We've got over, I think last count is 802 repeaters, I think, that are signed up, over 9,000 users now. Doug's the guy that takes care of all those numbers. He's assigned, so he knows exactly minute by minute how many people are on the system. Being that they used Motorola repeaters, initially get this thing started because you're talking about Motorola engineers that got this ball rolling back in 2009. Motorola repeaters have a IP site interconnect proprietary protocol, so only one Motorola repeater can connect to another Motorola repeater. However, any DMR Tier Type 2 portable or mobile can be used on this system.
Now, there are some other companies that make repeaters. There's Hytera as an example of a company that makes repeaters, and there are some hams that are playing around with linking up a bunch of Hytera repeaters. So there's more DMR than just the 800 Motorola DMR Mark network. So there's other networks and other isolated individual repeaters.
Being that in order to maintain system integrity, they don't allow anything as far as Echolink, any analog systems, D-Star and X-Edge and that sort of thing into the repeater system, crossband in or anything else. Managed capacity, it provides for the reliability of the system. This is just a pin map, just of the United States. It's not representative of all of them. It just kind of gives you an idea of the saturation. There's 22 countries now, 800 repeaters, 9,000 users, and all this growth is since 2009. The interesting thing about this is you've never seen an article in QST or CQ magazine advertising this stuff. I mean, this is all word of mouth, and people who are attending meetings like we're doing right now that find out about this and then get involved. This is part of the network architecture. It kind of gives you an idea how things work. The C bridge is what connects everything together to the internet. You have, for example, an Illinois master, a Nebraska master, a Florida master, and an Ontario, Canada master. These are just as examples. That's not all of them. For example, if you wanted to talk to Nebraska only, you would go to time slot 2, and the talk group is 3131, which stands for Nebraska, and you'd only talk to Nebraska stations, masters and peers. So we've got 5, almost 6 repeaters on the air now. If you have a Nebraska talk group, all those repeaters be tied together simultaneously talking on the Nebraska talk group. So if you're in Lincoln, you want to talk to Omaha, you get on Nebraska talk group, talk to somebody in Omaha, and vice versa. Another example, if you want to talk to the Illinois master and you're in Illinois, it would only pass traffic to Illinois and Nebraska if you're on the local talk group. We have that tied in so we can talk to the guys in Chicago because they work for Motorola, and it's but that can all change. I mean, we can change these talk groups from time to time and the access. However, then every repeater will have access to time slot 1 and talk group 3 with your international channels. So if you want to talk around the world, that's the way to do it. A little more simplicity on exactly how the C-Bridge kind of works. They use Smart Push to Talk. It's a different product in Europe, but it's able to be used, and so it's consistent with what we use over here and able to talk overseas there. New developments, you can see we have a Midwest frequency. Those are the Midwest channels. It's not a frequency, it's a talk group. Sorry. Each one of these regions have talk groups. There's multi-language talk groups. If you're fluent in German and you want to talk to a German talk group, you can go over there and talk in Germany. So that gives you a little extra flexibility. I'm running through this a little bit quicker because I'm looking at 9 o'clock. It's getting kind of late. Some new developments, they have a contact generator which allows you to generate a list of views from the last 30 days. You can put in your radio and see who called you, people that you've made friends with and that sort of thing over the air, other hams. You can log that into your radio, so that'll maintain a memory so you can always find them in your list of contacts. A lot of growth in New England states are kind of limited right now because they can't use any UHF repeaters because of PAVPAW. It interferes with the government radar systems up there, so they're using VHF primarily, 2 meters. Hawaii, I can remember when there wasn't one repeater 2 years ago in Hawaii. There's probably 14 of them now. I mean, this thing is just really exploding. Automatic ID system, that'll probably save Doug a lot of problems because he's the one that issues all the IDs for the entire system, and hams will be able to go right to a website and sign up and get their ID number so they can get operating right away. Have an audio test reflector. If you want to find out what you sound like, you can go over to time slot 1, talk group 999, key up, and you can hear yourself coming back. You know exactly what you sound like, whether or not your radio is over modulating, if it needs to come up a little bit, that sort of thing. Innovation, they just started this DMR sandbox where they're doing a lot of testing. If you want to find out how things work, you can go over to the sandbox talk group. You can experiment all you want, and some of the things that they really would like to see people develop in this sandbox would be FCC compliant APRS type positioning software, automated text messages for severe weather outbreaks, contact list expansion. Right now, most of them are limited to about 1,000 contacts. They're looking for call sign aliasing. Yeah. Anyway, and then some front panel programming. There is some products out there that allow you to do some front panel programming. But as it stands right now, you have to have a laptop and a programming cable. Primarily because the products are made for amateur radio. Yeah, go ahead.
What is call sign aliasing?
That's a good question. What is it?
Well, most of the commercial formats, the unit ID is a number. That's what Doug assigns.
Okay.
So if you got a radio and you want to put it on the network, you get a number. That's your number. It's like your phone number. But your caller ID, if I dial your number, it shows, so that's an alias. It's a name or other information like a call sign that's associated with the ID number. And you can put that in here, so when Frank talks, it can say Frank or no good scoundrel or whatever you want it to say.
Okay. Thank you.
We have some nets that are very helpful. You're not going to find anybody who's not a nice guy on this system. I have not seen anybody who's arrogant. or anything else. Kind of contrary, because a lot of times you run those people on different nets on amateur radio. There's a worldwide user net that's on Talk Group 1, time slot 1, 11 o'clock Central, every Saturday morning. There's a tech net, which is really interesting. If you have any questions, and there's no such thing as a stupid question, only stupid answers. So if you want to find out what's going on, or you have a question about programming radio, or just anything that comes to your mind, you can get on that tech net and ask the question, and somebody's going to come back to you and give you the answer. We haven't initiated this one yet, but it's in the works right now in Nebraska Net talk group that we've had at 8 o'clock on every Tuesday evening. So here's the local repeaters. That's where they're located at. These are in the system right now, except for AAI's. This is still kind of in the planning stage right now, but that's it's going to be getting on the air soon, right? Okay, as soon as you get your coordination and everything. Downtown Omaha, Weeping Water, Bellevue. These were in the orders that they actually came on the air. We put the one up in Lincoln the first week of April, and Kevin just put his up out there on 105th and the Interstate, and RJR's got one down there in Nebraska City. His son, of course, had the second one on there, HYI, George Jr. Okay. Let's move on over and do a little demonstrating with the radios here, and then you get an idea of what this stuff is capable of. What we're going to show you is that both of these radios are operating on the same frequency. They're operating on the same repeater, except that this is going to be operating on time slot 2. That one is going to be operating on time slot 1. So you're not going to have any collision here between the radios, because this is using one half of the band, and that one's using the other half of that frequency. Okay. So if Kevin, Doug, you give me a hand with this. This is go out there, make some see. This is set up on worldwide right now. So go ahead and get going with that, and turn this light on here. And this is on.
Quick demonstration.
No, this is on scan.
AI0PY in Nebraska.
Scan off. Okay, it's Nebraska. Midwest. WB0QPK on Midwest talk group and way around. WB0QPK for a signal check and demonstration.
We'll sleep in Europe.
Could be.
AB0 ZZT. Independence, Kansas.
George, we're down here at the Amateur Radio Club meeting at the Red Cross, and we're just talking on the same repeater. Kevin's over on time slot 1, I'm on time slot 2. We're carrying on a conversation here, kind of giving a little demonstration. How's it sound down there in Independence, Kansas?
As if we're sitting across the table from each other.
Yeah, sounds good.
Well, Kevin was talking to some other station. I think he was on worldwide at the same time. So that's kind of what the point that we're trying to prove, is that you can have one frequency operating through one repeater, but we're on different time slots, which allows us to carry on conversations at the same time.
Yes, sir. I just heard another radio worldwide, and I hear him talking. Sounds like he's across the table also.
Frank, is there any kind of a delay in key up when you
Just very slight.
okay, I figured it would sound.
Like most systems
Sure.
that are going through the internet and that sort of thing.
Sure.
It's not like 3494 where you just key up and be there.
Exactly. Yeah. Okay.
WB0 QQK on Midwest, anyway around. Needing a demonstration here on motor turbos. WB0 QQK.
This is GBS something Ohio. My name is Jeff.
Okay, Jack. We're sitting here in Dayton, Ohio.
About 15 miles south of Dayton, yes.
Now you see that we're on the same repeater, and so we're here on 105th Street.
Yeah. Here's one of the folks checking in with Kevin on North America Talk Group now. I think I even heard some folks in Chicago calling. KB0ZZT.
CD022K, Frank, this is Chuck, W4CLL, Fantasy Florida.
Well, that's why my ID's coming up, that's why he's...
This is WPLC, have a good evening.
Very good. Appreciate the comeback here and opening up some eyes here. I think people are kind of interested that we're talking through one repeater and we're on different time slots here. We've got 2 stations set up here side by side, probably about 20 feet apart.
That's the beauty of DMR, friend.
Anybody want to step up and do a CQ here? You can sure do it.
Was George in there?
George is on there, right?
To really be useful in emergency communications where you have to have simultaneous conversations and still do it on one repeater. Storm watching, regional emergencies and stuff like that. KB0ZZT.
If you can punch up 440.
Good evening, George. This is K0CTU on Frank's Radio. You're in Independence, Kansas. Yeah, we're up here at the Aksarben ARC Meeting. Very good. Pretty interesting program, and the audio sounds awesome.
This one's
K0CTU.
on top group 1, he's on top group 2.
Yes, Matt, I really enjoy this. I own 2 DMR repeaters, one in Bellevue and one down here in Kansas. And I've been in Dayton Hamfest the last 3 years, helping staff the DMR information booth there. Directly located across from the WRL area, KB0ZZT.